Lesson 42. Recording an Earthquake. First listen and then answer the following question. What does a pen have to do to record on paper the vibrations generated by an earthquake? An earthquake comes like a thief in the night, without warning. It was necessary, therefore, to invent instruments that neither slumbered nor slept. Some devices were quite simple. One, for instance, consisted of rods of various lengths and thicknesses, which would stand up on end like ninepins. When a shock came, it shook the rigid table upon which these stood. If it were gentle, only the more unstable rods fell. If it were severe, they all fell. Thus the rods, by falling, and by the direction in which they fell, recorded for the slumbering scientist the strength of a shock that was too weak to waken him, and the direction from which it came. But instruments far more delicate than that were needed if any really serious advance was to be made. The ideal to be aimed at was to devise an instrument that could record with a pen on paper the movements of the ground or of the table as the quake passed by. While I write, my pen moves, but the paper keeps still. With practice, no doubt, I could in time learn to write by holding the pen still while the paper moved. That sounds a silly suggestion, but that was precisely the idea adopted in some of the early instruments. Seismometers for recording earthquake waves. But when table, penholder, and paper are all moving, how is it possible to write legibly? The key to a solution of that problem lay in an everyday observation. Why does a person standing in a bus or train tend to fall when a sudden start is made? It is because his feet move on, but his head stays still. A simple experiment will help us a little further. Tie a heavy weight at the end of a long piece of string. With the hand held high in the air, hold the string so that the weight nearly touches the ground. Now move the hand to and fro and around, but not up and down. It will be found that the weight moves but slightly or not at all. Imagine a pen attached to the weight in such a way that its point rests upon a piece of paper on the floor. Imagine an earthquake shock shaking the floor, the paper, you, and your hand. In the midst of all this movement, the weight and the pen would be still, but as the paper moved from side to side under the pen point, its movement would be recorded in ink upon its surface. It was upon this principle that the first instruments were made, but the paper was wrapped around a drum which rotated slowly. As long as all was still, the pen drew a straight line. But while the drum was being shaken, the line that the pen was drawing wriggled from side to side. The apparatus thus described, however, records only the horizontal component of the wave movement, which is, in fact, much more complicated. If we could actually see the path described by a particle, such as a sand grain in the rock, it would be more like that of a bluebottle buzzing round the room. It would be up and down, to and fro, and from side to side. Instruments have been devised and can be so placed that all three elements can be recorded in different graphs. When the instrument is situated at more than 700 miles from the earthquake center, the graphic record shows three waves arriving one after the other at short intervals. The first records the arrival of longitudinal vibrations. The second marks the arrival of transverse vibrations, which travel more slowly and arrive several minutes after the first. These two have traveled through the earth. It was from the study of these that so much was learnt about the interior of the earth. The third, or main wave, is the slowest and has traveled round the earth through the surface rocks. H. H. Swinnerton, The Earth Beneath Us.
Lesson 43. Are there strangers in space? First, listen and then answer the following question. What does the uniquely rational way for us to communicate with other intelligent beings in space depend on? We must conclude from the work of those who have studied the origin of life that given a planet only approximately like our own, life is almost certain to start. Of all the planets in our own solar system, we are now pretty certain the Earth is the only one on which life can survive. Mars is too dry and poor in oxygen, Venus far too hot, and so is Mercury, and the outer planets have temperatures near absolute zero and hydrogen-dominated atmospheres. But other suns, stars as the astronomers call them, are bound to have planets like our own, and as the number of stars in the universe is so vast, this possibility becomes virtual certainty. There are 100,000 million stars in our own Milky Way alone, and then there are 3,000 million other Milky Ways, or galaxies, in the universe. So the number of stars that we know exist is now estimated at about 300 million. Although perhaps only 1% of the life that has started somewhere will develop into highly complex and intelligent patterns, so vast is the number of planets, that intelligent life is bound to be a natural part of the universe. If then we are so certain that other intelligent life exists in the universe, why have we had no visitors from outer space yet? First of all, they may have come to this planet of ours thousands or millions of years ago and found our then prevailing primitive state completely uninteresting to their own advanced knowledge. Professor Ronald Bracewell, a leading American radio astronomer, argued in Nature that such a superior civilization, on a visit to our own solar system, may have left an automatic messenger behind to await the possible awakening of an advanced civilization. Such a messenger, receiving our radio and television signals, might well retransmit them back to its home planet, although what impression any other civilization would thus get from us is best left unsaid. But here we come up against the most difficult of all obstacles to contact with people on other planets: the astronomical distances which separate us. As a reasonable guess, they might, on an average, be 100 light years away. A light year is the distance which light travels at 186,000 miles per second in 1 year, namely 6 million miles. Radio waves also travel at the speed of light, and assuming such an automatic messenger picked up our first broadcasts of the 1920s, the message to its home planet is barely halfway there. Similarly, our own present primitive chemical rockets, though good enough to orbit men, have no chance of transporting us to the nearest other star, 4 light years away, let alone distances of tens or hundreds of light years. Fortunately, there is a uniquely rational way for us to communicate with other intelligent beings. As Walter Sullivan has put it in his excellent book, "We are not alone." This depends on the precise radio frequency of the 21 centimeter wavelength, or 1,420 megacycles per second. It is the natural frequency of emission of the hydrogen atoms in space and was discovered by us in 1951. It must be known to any kind of radio astronomer in the universe. Once the existence of this wavelength had been discovered, it was not long before its use as the uniquely recognizable broadcasting frequency for interstellar communication was suggested. Without something of this kind, searching for intelligences on other planets would be like trying to meet a friend in London without a prearranged rendezvous and absurdly wandering the streets in the hope of a chance encounter. Anthony Michaelis, Are There Strangers in Space? From The Weekend Telegraph.